Hello everyone, welcome to this tutorial. In this episode we're going to talk about dynamic programming and penalty propagation. So let's recap the last episode. We're talking about how do we minimize the cost function. The cost function here, the overall with the color information and the spatial smooth constraint. And this is not a traditional way we're going to do because it's horrible. Before we proceed to today's episode, we're going to recap a little bit the procedure. We're going to how we compute the sensor transformed cost map. So this is the code and the FPGA code, and just to give you a little feeling about what is happening. It's exactly how we get this data layout. Okay. So so this is the 3D points XYZ in the 3D dimension. There are two projections. One is P in left image pixel, and the other one is P prime in the right image. Okay, and this is P in the right image corresponds to the right position. The position in the left image means that the horizontal length is the same here. From here to here, it's the same from here to here. And our job is to find the corresponding point, the P prime, along this to the left. We are searching for 64 candidates, right? So after we search for 64 candidates, then we will have this sensor transform cost map, and it has 64 candidates, and each candidate has the bit width. In my FPGA code, I give it 6 bits because 2 to the power of 6 is 64. So the maximum, if you add all the ones together, the 63 bits, the maximum value will be 64. So the 6 bit will be enough. Okay, but in CPU, when we design the C++ programs, because there's no 6-bit fixed point, so you have to use the 60 bits or 8 bits or like the it's a multiple times of 8 bits the length in the CPU when you design the algorithm so you have to be aware of this difference between CPU and FPGA. Okay, when you do the algorithm design. Okay, so now let's record XOR operation. So this is the feature map on the left. Suppose we have feature map that's after sensor transform. Suppose this is after sensor transform, and this P is not the original. It's not the original image, but it's a features vector that encodes the so this is a feature map. This is a feature map that encodes the color information, that's color relationship with its neighbors. Okay, so I repeat again here. And now we are finding, we are using the XOR operation. This is feature map. Each one is 63 bits long, and to do XOR operation from to the left to 64 candidates, left image, right image candidates. Then we hopefully we will find this P prime using this information, using the color information alone. it means the sensor transform alarm. But as we have mentioned in last episode, it should not be enough. We should have to it would be better for algorithm to consider this smooth constraint. Okay, so now our purpose of this matching color cost is to get this CT cost map. That is a pretty large memory in a chunk of memory in the CPU or FPGA. So you have to store all these data. Okay, so now we're going to talk about how we get this big chunk of data. Okay, so now to simplify things, we assume that the depth of the sensor transform's output is not 63 bits. It's not 63 bits, but it's 4 bits. Okay, and now say we know this point in the left image. This CT sensor transform vector is 0010, and that one in the p-1 in the left image, the second candidate here to the left, one disparity away, 1 pixel away, it's 1010. And then we will have when we do this XOR operation, first do this XOR operation, this bit by bit, 1 0 becomes 1, 1 0 0 because it is the same, and the 0 goes down here, 1 and 1 because it's also the same, so it's also 0, and the other bit all 0. And now we count the ones in this after this XOR operation. So here the number of ones is just 1. So this is the color cost matching for this pixel P in the left image, and the disparity is to the left, one pixel away to the left. Okay, so this is the one here. So this value here goes here. This is the value here. It's then you put 1 here. Suppose we still use the 6 bit for each of these elements. Okay, 6 bit. Now, and let's do another example. Okay, now let's compute CP0. This one, this one. Now we have already computed this one. Now we're going back a little bit to the very first element. The disparity becomes 0. Then when the disparity becomes 0, and you do the same procedure, and you got the counter numbers you get 2. So CP0 here is 2, and this is 1. And you do another one. Oh, sorry. I need to choose 2. Suppose the 2 is the minimum one. Okay, suppose the 2 is the minimum one, then the CT feature map in the right image, p-2 here, it's like this. It's exactly the same as the p1 in the left image. The sensor transform feature map here is the same, so it will become 0. So this position CP2 will give this minimum, give us the minimum CT cost map. Okay, so if we don't consider the space constraint, then we directly finding the minimum here. That will be here, and this second one disparity becomes 2 here. Okay, so but now we already know that we are, because we are going to add a spatial constraint, so we have to save this information aside, and do more, consider use it as a source to the next stage. Okay, so that will be will be this one. So we input this string here to this, all this map string one by one to this module. The streaming is in the FPGA process is streaming, not stopping. So this is as a source, and we go into this. But in CPU you have to save this aside. After this stage, then you starting from this point and fetch the data from the memory, DDR memory, then fed it into this module, and then save this output chunk of the memory in the DDR memory again. But the FPGA is a different way. It's a streaming, and we will talk about this, how to do that, because if you do the DDR memory fetching too often back and forth, for the FPGA will be too slow, okay, or also too tedious. In FPGA, if you consider it the streaming way, you use the LAN buffers kind of the technology, then you will avoid to saving this intermediate chunk of data back in the DDR. Okay, we will talk about this technology and then in a later episode. Okay, that is the procedure of how do we get this chunk of data, the city cost map, memory layout, and we are going to use this data in this episode. Okay, and this is the C++ code, and you look at that. This is the XOR operation, and first bitwise compare. Here, bitwise compare, then you count in the number of ones in the compiled result. Okay, also we will talk more in detail later episode. I'll just point out that we're using 64 bits here, because the CPU doesn't support 63 bits of fixed point. Okay, that's you have to be aware of this when you design the algorithms. So you have to be aware how you store the data in one like 64 bit integer. You still have one bit left. You didn't use that. You have to know how you align all this data. Okay, so now let's get back to this dynamic programming. We talked in the last episode that dynamic program is a way to minimize the overall optimal. It's subdivided into several small chunk of optimization. Then together we got maybe it's a suboptimal result. Okay, this is the idea of this dynamic programming. Okay, so in today's episode we are going to talk about how we go from this formula, which has obvious physical meaning, to this. This is the formula you can read it from you can get it from the original SGM semi-global matching paper. So but in that paper it's not very it didn't list very clearly how he derived from this place to this formula to this formula. Okay, so there's a middle place. It is the omitted. So I'm going to show you how to very easily also naturally if you design an algorithm, how you optimize your algorithm. Maybe you do some research and experiments, and you go to the middle intermediate point, and you find out, okay, there's some improvement. Later you got the idea how to solve this problem. Then you get to this result, get to this semi-global matching algorithm. Then you write a paper and say, okay, this is a great thing you have discovered. Okay, so this is a system block diagram so far, and so we are here, and today we are going to tell you how to derive this chunk of memory data, this output of this just this overall cost. Okay, this is the matching color cost, and this is overall cost, combining color information and the spatial constraint, and you will get the overall cost. And from this, then okay, and also we only talk about left cost, and in the next episode you don't have to go write another module for the do that write module write cost, because you can derive directly from this chunk of memory to get this write cost. That's kind of the very interesting technology, okay, technique, and I also will show you in the next episode. Okay. Okay, so I'm not going to repeat this again, the dynamic programming, just read this about these notations, because it's very important, because we should be on the same page, and you should have, maybe you have your own habit to notate things, but I just to tell you that this is how I do this. And you be note that this D means for disparity. Consider as an x variable when you do the functions, when you do the math, is a variable x. So but I write it in many variants. Actually they are same. You consider it's a register in a CPU. So I just give it another name, but when you call this, you point to the same place, same register. Okay. So, but the good thing about writing in it with a upper subscript, I don't know whether this is subscript it's right or not, because I haven't searched online. Okay. So subscript means what I mean is on the upper right. Okay. I don't know whether this is right or not. It's a counterpart to sub sub just under. Okay. So that you got what I mean. Adding this, you just want to make it meaningful, so that it's easy to understand this what is variable is associated to. For example, here, if you added a p, means that this disparity is a disparity map. You have 64 candidates for this pixel, left pixel p, and also for this one you have to and you have used this disparity, 64 disparity candidate is for the pixel q. Here q is a neighbor pixel for this pixel, and also subscript here means direction. It means is okay. I'm not going to talk too deep. You mean it's the same thing. It's just that it's you understand this also. Don't be confused. Just say it's when you see this, don't be scared. It's just it's just a language. It's okay. When you see this, just think of this image. You will understand better. Okay. This is disparity, and this is disparity, minimum disparity. Mean subscript means that this disparity can make this overall cost function becomes a minimum. Okay. That's what that is that. Also, if you see this notation, that is because something is wrong. Because I make a mistake. This, if you see I in the subscript, D is something that means the P, Q, R, P, R, something like this. It's a right thing, but this I thing is wrong. So the subscript I is added by mistake, so you can remove it, or you just ignore it. Okay. So here I also, if you see I here is also from 0 to the disparity, maximum disparity 64 minus 1 is 63. In this tutorial, only my project is 63. Maybe other people's project they have the 128. Okay, etc. You can. So for instance, if you see this, it's wrong. You have to remove this I and put this dp down here. Actually, you can say dp0 is equal to I. I don't know why I make such a silly mistake here. Okay, so you become this dp0, dp sub p0 is from 0 to 63. Okay, so you search the mean and search the minimum. So this is color match color cost. Okay, sensor transform cost matching map. Okay, sorry. Okay, so you're searching in this. You're searching on it for each pixel p. Each pixel p, you are searching from 0 disparity to 63 disparity. Okay, so you find a minimum and you get this disparity for that pixel. Okay, that is what it means. Oh, now let's talk about the chicken egg problems. What I mean by that is that suppose that we are calculating this. We are trying to find the, we're trying to calculate the. Okay, so our purpose is to find the this overall cost for this pixel p. Okay, so now suppose we know its neighbors. You have q0 to q7 neighbors. Suppose we know its suppose the neighbor is already had calculated this overall cost function as q0, dq0, and all of them have already known. Suppose they are known, and now the minimum is also known. So this disparity mean is also known. So this is a disparity mean means that this is the right z and spatial spatial information they already know. Now according to this second term of the spatial smooth constraint, now since what they are known, now then it should be quite easy to find a minimum for this pixel p, right? Because for when you add an all together and to make a for each candidate, 64 candidates, you put all this information in for the information in. For instance, here is all the neighbors say, oh no, I will give you p2 for penalty because it's too far from us. So you will find you will later find this place, maybe this place. Okay, maybe in the middle or something to agree with all of your neighbors in a spatial constraint. Then you will get this overall cost for this pixel p, and you will find this pixel p's minimum disparity. And that is the ideal situation, ideal case. But now because p is now when we calculate p, q0 to q7 is neighbor, but when you calculate q0, p is its neighbor. So it's kind of you're sitting on a loop. If you want to calculate p, you first need to know q. But if you want to calculate q, you need to first know p. So it's a chicken and egg problems in the loop. So how can we break this loop and make this problem separable? So that is the most of when in the physics, when you research something, you want to make this equation separable, so that they are not in a loop fighting each other. So we make an assumption that okay, now since this you are on a loop, but can I decompose my overall cost function SPDP into a components, and each component is determined by its corresponding neighbors. So and it's relevant to other neighbors, so that so this one. Sorry. For instance, for now, let's take this r equals to 0 in this direction as an example. Now it's only a function of this Q0 pixel, Q0 neighbor. So other neighbor is irrelevant. It's you also can say it is independent with or orthogonal to other information. So so that now and L1 is only a function of this is neighbor Q1. So you have these 8 components here, 8 component here. So this for the last component is only have to, is a function of this Q7. So now you get the idea. You decompose this problem one step. Okay, so if we know this now if we know this the neighbors, then we can get this. We can calculate this each component and sum it up to get this overall cost function. But unfortunately, it's still a chicken and egg problem, because for this pixel Q0, you still need some information from you, right? From pixel P. Okay, so for instance, in what direction? Because for Q0 you have maybe in Q0's perspective, P is Q7, so it's in this direction. Okay, so he has a contribution to Q0's is the L7 component. Okay, but now P is unknown, so his component is unknown. So the Q0 overall is also unknown, also can be known. Okay, so there will be this is infeasible as well also. But now we can go another further step to make another assumption that since this pixel and this neighbor, they are all can be decomposed into 8 components. And what about in each components in each corresponding dimension, they are only relevant to each other. For instance, now L0 P for this P for pixel P, this L0 is only a function of Q0's zero dimension. It's not overall. So in the previously is overall pixel QR information. QR means Q0 is a whole. It's a some overall means that it's a function of this term. But say not make this function of this term. Can we make this function of this corresponding component here, LR? Okay. So now if you can make this further assumption, then this problem will be fully separable, because if you look at carefully, you will have this one direction line, multiple direction lines from for instance, the top right to the bottom top left to the bottom right, and from this direction. So now if you know the minimum of this one, L0, minimum of L0, not this one. Okay, in the previous assumption, we have to know this overall minimum. Okay, overall minimum of this neighbor Q0, the summation. So not this component. Okay, so now if we say that make assumption that this component is only have to take into using this component as a reference. So if you know this dimensions minimum value, then you got this disparity in this dimension as Q for this pixel Q0, and in this dimension, 0 dimension, you know its position, then you can predict that okay, in this dimension your position should be around this position. Okay, so I will give you a penalty, and so then this will be fully separable. You don't, okay. So look at this notation again. Q means is neighbor, and neighbor index. For instance, Q0 index is 0, Q0, and Q1 index is Q1, neighbor index, and also the direction or component index as a substitute here, 0 and 1 here, down here. Okay, so this is a notation for things, but we can further simplify it because you have two and this index, two indexes are actually the same value. So component or direction index and this neighbor index in this case is they are the same, 0 0. So we can say why not just use Q0 for simplification. Okay, I hope you got the idea. Anyway, just language to when we talk about human language, it's quite easy to understand, but how to use math to precisely or in a tedious what to say? But it's literally tedious, and I mean that to say that in the more precisely way. Okay, it's just a language. Okay, so don't be scared by these numbers and annotations. Okay, so now I think you got the idea how to decompose SP DP for this target pixel. Okay, it should be now quite obviously, and now this is a decomposed version LR. It's actually just using this. The spatial constraint relationship is the same. You just substitute this variable. How to write a variable? This Q becomes QR, and P becomes PR. In R means direction, Q and okay. Okay, so that's this, and also you decompose the neighbors is the same way. Now, let's show you how to write a code, to implement this so far. You actually can use this to design the product, but which is actually when you're in the market, you already see people using that stereo vision, only the color information to design the prototype, but the result is not that not that surprising, not that optimal. So now that you have this straightforward spatial constraint formula. Now you can add in this together with this information cost sensor transformed cost map. So you can write a code for each path, each direction, and then adding up to get the overall minimum location to find this disparity for this, to minimize this overall cost function. Okay, so so for the 0 dimension, you need to know its neighbor Q0's minimum disparity position, and for L1 you need to neighbor Q1's minimum disparity position, and then you using this to add this penalty value, and you get this get the overall cost map, and in this overall cost map you're searching for the minimum. You got this disparity for this pixel P. That is the disparity value for that. Okay, and you will get, according to this disparity, you can find out the distance of the pixel in the 3D dimension, in a 3D space. Okay, now let's run this code. First, of course, it's a spatial smooth constraint CPU. Okay, here Let's see first using the bypass one. Okay, let's see what's the result. This is the what's my computer. Wait a second. Control key is somewhat being hacked, so I cannot use control. That's nasty, these hackers. Okay, now let's make a left image and right image. Okay, this is a disparity, and this is a grayscale, and this disparity corresponding to the left image here. Okay, so actually it's the same one here. I don't need to open this one. You already this one here without a smooth constraint, only color information. So you see the result. Okay. Now let's add a smooth constraint, only left label spatial information. Yeah. You see here is adding all directions together, but actually you don't need all the directions. Okay, because in FPGA there are some directions you cannot use that, because in a streaming way, you know, there's no way you can do that in some direction. And also we'll talk about this later. Oh, it's a little bit cold now. And let's add this spatial smooth constraint. And let me show you the code here. It's really nasty. The spatial constraint and left scan. Here I only do the left scan. Okay, so after you finish this episode, you should quite easy to understand this code, and depth wise, I should say disparity wise add, not depth wise add. So I only add this left scan, and you can do the other scans as well, and then add it together here in this step. Okay. So this is the when you add this kind of smooth constraint here, it's corresponding to this page, and the penalty value here is penalty 1 is 3 and penalty 2 is 10. So you can play around with these penalty values actually yourself, and to see what give them best output. That let me show you one result. What if the penalty P2 is too large, and what would become? Say we add this, becomes 60. So so you can look at this formula and make a wild guess what will happen if this P2, if P2 is too big. Okay, so and this term will become a little bit dominating. And if the noise is too big, is there any way to this one can drag this cattle or maybe something like animal back to the right track? I think it will be very hard to fight because these two terms are fighting with each other. Okay, we should make this color constraint a little bit dominating, because the color information is a little more most of the time is more reliable. Okay, so let's see what. Let me show you the results. Okay, see, as I said, it's so it's like a from the very beginnings of to the left scan to the right. So all the pixels considered in the left, it's a one-way history information, and so the minimum position of the last pixel has a lot of say in the next positions disparity value. Okay, so if the previous left pixel is wrong, label is wrong, then if the penalty is too big, then the right info, even if the color information gives the right position, but because it gives a little bit penalty, P2 is too big, it will favor the noisy most of the time the noise position around this label. I say because it is because P2 added to this very large. Okay, so that's why what happened in this case scenario. So now we had ask ourselves how to any way to recover from this noise and giving color constraint. Actually, this is the starting points why the SGM semi-global matching, the author has come up this algorithm, because his motivation is just to solve this phenomena. Okay, because when this penalty is too big, how can we recover from the middle of this when the color information is accumulated enough, enough, then you will drag this animal back to this right track and do. Okay, so that's the starting point, and how we this is a problem we are trying to solve, and also you can say this is a pain point. Now, to come up with this come up with the author's formula right away, and let's first start from analyzing the data, explore the data first. Okay, this is how most people do deep learning. It's exploring data, so to get a feeling what caused this phenomena. And okay, so now let's analyze this. Let me stop this first. So analyze a special scenario for the solution. Now, again, for this zero direction, you have the label Q0. Okay. So suppose we know Q0's this component, zero components overall cost function, and its minimum position is here. This is the first minimum position. Now we are looking for several minimum positions, second, third, or maybe up to 10. Okay, so suppose this is the second one, And our objective is to looking for this one, L0. The same components can only compute the same component. Zero component can only compute the zero component in the next in this direction. Okay, in this other direction. So it's easy to understand that our objective is to find out this dash line as a dash line value. Okay, and now since we already have the color information, now this information is known. See, cost sensor transforms cost is known, and its minimum value is here. It's at this position dp0, and it satisfies this cost functions, sensor transform cost function, looking for this p for this pixel p. And there's a relationship between this this dp0 mean with this first mean and the nth mean, or second mean, we can say a second mean. So it's more, unfortunately, it's more close to this second minimum, nth minimum. So it's less than 1. That disparity is less than 1. For instance, that's okay. And to this minimum position, to this neighbor is far away, and it's greater than 2. So obviously, if you take into the spatial constraint into account, you get the penalty of a P2. That's very large. So it will happen like the in the last slice. It will give you the wrong position in here. So all the image will be disaster. The output will be disaster. So and now suppose we know that this should be the right. This is actually, we know is the right disparity for the last pixel, but it's because of some kind of reason, some kind of accident, or maybe noise, something. He becomes the minimum one, and he becomes the second one. And how can we tell the algorithm that I want to choose this one over this one to calculate my current pixels minimum disparity, or disparity cost, the overall cost map. Okay, so the solution is that when you look at this curve, it looks like a. Can we interpret it as kind of the probability of being the disparity, right disparity? For example, this is the minimum, and it's inversely proportional to that probability. When it becomes minimum, it means it's high over 1. It's highly possible that this is the possibility, that it's very highly the possibility that this is the right disparity position for Q, for this neighbor Q0. Okay, so okay, so now let's now, but we haven't used this information, right? Previously we only used this minimum. If after we calculate the minimum position, we scatter this other information away. We only use this one. That's why we can do a disaster, because when it's noisy, when it's corrupt, contaminated. But if we kept this all the information, because it's coming from all the processes. Okay, what's the right way to say it? Predecessors on this direction. Okay, so it's kind of it has accumulated this history information, or meaning the path information that ratio this all the previous predecessor says that this is your being you're being in the right the minimum position of the disparity. This is probably information for all your pixels, all your depth disparity of candidates, their probability. Okay. So now we can use this information together with this penalty So we come up with the penalty propagates. Okay, so it's like this is the penalty itself. This curve is the penalty itself. It's propagated from the very first points, very first pixel, and the edge of this image. Okay, starting from the edge of the image, and we define this penalty propagate value as this one, this curve subtracted by its minimum value. Okay, this is the curve here. We move here, and subtracted from the minimum is we want to remove the comma bias, so there's no bias there, bias value here, to save a lot of bits and FPGA resources, because you don't have to store the not useful information. Okay, so the total penalty now becomes the penalty propagated from the history, from the predecessors, and add this spatial smooth constraint. I will explain this meaning. Okay. Now our penalty, this component's zero components cost function will become it's the same. We didn't change this formula, but we're using little we adding this selection here, multiplexing here. This is a traditional one. We only consider the first minimum position. Now we add another. We compare it to another minimum position. Because, for instance, second one, we say if this one is the right position, what's the penalty what's the penalty it will give to this position P, to this pixel P. And if this penalty is smaller than this penalty given by this smallest one here, we will say that we will say that this is noisy information from the past, because he obviously agree on with this color information for the current pixel, right? So the messages, you can interpret the message in the like a frequency perspective and time domain perspective. Actually, they are the same message, just interpreted in different dimensions. So they should agree with frequency domains and time domains should somehow they should agree with each other. This is the same. And the spatial domains and this color domain, they should agree with on each other. So we said this one should be the right position. And so that's why we need to adding this multiplex and selecting this minimum. Compare this minimum, this penalty, total penalty, with this total penalty to that minus one. So if we consider not just one minimum, 1 second minimum, maybe we can add up to 10 or 20, and then you can compute many of this kind of. But in this paper, they consider they compared all the rest of he's more greedy. He compared all the rest of candidates. So you are not smallest. But I think you don't have to compare the original. But in my FPGA implementation, I using the stick to the original one. But you can save some some resources. So you can only compare it to this, maybe the 10 or 20. You compare, you get these candidates. You compare it to them. There will be it will be enough. I think they will be adequate. Okay, so now this is our new cost function for the overall cost, but we adding we adding this to compare with this. Just find out. Is to just to see if we can recover it from this from the noisy information. Okay. Okay. So now question is how to compute this total penalty. Okay. So remember this total penalty is a penalty propagated from this one, and adding this smooth constraint. Okay, now take a computing this L0P as an example. I think this should be Q0. Should be Q0. Sorry, I make a mistake. Should be Q0 because this is a pixel Q0 and Q0 and Q1. Okay. Anyway, you understand it. It's not just Q. It's Q0 here. This is Q0 here, dump here. Okay. Otherwise, you will, because if you use Q to represent neighbors, then you have 8 neighbors here. Q0 to specified is that neighbor. So here we're going to compute. Now let's first compute the total disparity given by this second minimum point of this neighbor Q0. Okay. Now so this curve itself, this value here minus by this minimum will become here. So this is the penalty propagates value. Also the penalty itself. So if this penalty is small, that means that it's highly possible that it's possible that this is a right disparity for this pixel Q0. Okay. And P1, what's the value for P1? Because it's close to, because their distance is less than one pixel, right? So it should be P1, penalty P1. And now sorry. Okay, so okay. Now let's compute this from this first penalty the same way, and this is let's compute the penalty propagated from, okay, should be 0, okay, because it's minimum. It minus itself, it's become the minimum. The only term left here is P2, okay, but the P2 is very large, okay, P2 is very large, and the P1 added to this penalty propagate is still less than P2. That means that, okay, this one is, we select this one and we drop this one. That means from this point on, the history no longer dragging this to the hell. Okay. So this is how the procedure of how to compute, and the same procedure it applies to any arbitrary, P0. And if you want to compute other just like this paper says, he computes every rest of the disparity candidates for this kind of things. So it's a very large the memory chunk. You have to store all this so. And now after that you know this is the cost map, overall cost map. Then you have this here I use 8-bit to a bit. In my FPGA code, I use a bit to store the result. I have guaranteed that it will not overflow. Okay. And then searching the minimum here in this along this disparity candidate disparity direction. Okay. And this is the count. Okay, so okay, we add this term here. We say just this term assumes that is the minimum term is contaminated and hot. We want this term to recover it. Okay, so that's that. The cost function from the SGM paper, the original one. I guess now that you should quite obvious you understand it, because you can see the shadows of penalty propagation and spatial constraint term here. This is spatial constraint term 0, P1, P2, and this term minus the actually this term is the minimum. It's just pointing to this one, this position. Okay, because this k is indexing from 0 to minimum. She's searching for minimum. This what this function say. This formula says is searching for minimums. If it is current for this current disparity position in P, and looking for the neighbor compared to all the neighbors that far away from us, from 0 to the left limit to the right limit. It's of course it's a little bit confusing, because when you're sitting in a D, k if the D is not in the middle, then sometimes you will reach into the out of the image. Okay, so that's a little bit confusing notation here. Okay, not mathematically stream what's the word for that? I mean the precise way to say that. Okay, so I mean that when it's considered, you understand, when you understand this is a minimum, it's actually doing the same thing. It's removing the bounds, and so that you into the each term then becomes this penalty propagated curve over the probability propagation something. If I prefer to use probability to interpret it, because it's much more physically understandable. Okay, so yeah, so you can read all this. This is what you can after this, I guess you play around this a little bit. You come up with your own version of your own variants of this automation. Anyway, it just the starting point is just how to recover it from this from this place. Now that we can, let's look at the code for this modified version. And previously we only consider this mean. Okay, Q0's mean, it enables minimum position, minimum disparity. Now we are considering arbitrary position from the candidates from the rest of the in the pixel in the paper. You consider the rest 62 candidates, but I say that maybe you just only take into account several maybe 10th minimums or 20th minimums. Okay, so to save a lot of computation. So now that this component becomes a function of not just this one, but this one, several of lengths, the function of that. Okay, so that's so that after compute that, you the same way you add up, you will get this pixels disparity. And now let me show you the code and to see. Okay, let me show you the code. Let's see. Oh, better this slow.